So with that, I would like to start my dissertation defense, the biomechanics and fluid dynamics of amphibious locomotion in Microvelia. The motivation for my project is bio-inspired design, and bio-inspired design shows up in many different systems. For example, on the image in the upper left-hand corner, we can see an image of a beaver, and beaver fur has inspired the design of materials for wetsuits for better temperature regulation when you're in the water. In the upper right-hand corner is an image of burdock burrs, and these burrs have inspired the design of Velcro for that hooking mechanism and unhooking mechanism. Shark skin has inspired the design of swimsuits. And lastly, my favorite, termite mines have inspired the design of buildings for more energy efficient temperature regulation. And so for my project, we're studying water walking insects for the design, to inspire the design of robots that move on the interface of water. And in this bottom left-hand corner is an example of that. So this specific robot was inspired by this insect right here, known as the Garidae. The Garidae uses its two middle legs to simultaneously row across the surface of the water. And it does this using surface tension. So it deforms the surface of the water without breaking it and allows itself to propel itself forward. And this insect has inspired the design of numerous different robots that move on the surface of the water. One caveat, though, is that this insect, because of its rowing gait, loses a lot of performance when it's moving on a solid substrate. So you can see in this video here on the left, as I'm poking it to try to get it to move, that its speed and ability to move is greatly diminished on the surface. This then begs the question, is there an insect that can better move on both water and land? So this then introduces the Microvelia and its amphibious locomotion. In this video here on the left, you can see this tiny insect, the Microvelia, moving pretty fast speeds. Despite the fact that it's only about 2 to 3 millimeters in body length, it is able to accomplish speeds of about 14 centimeters per second for its maximum speeds. And so that ultimately equals about 50 to 60 body lengths per second. But the Microvelia is also able to move on a solid substrate. So on this surface here on the right is styrofoam, and you can see that it's still fairly comfortable on this substrate as well, accomplishing speeds of about 10 centimeters per second or 40 to 50 body lengths per second. And it does all of this using just one gate, the alternating tripod gate. And this is the same gate that ants, cockroaches, and many other insects use to move about in its environment. When we look at this gate plot here on the left, the color bars indicate the moment in which the Microvelia's leg is touching the ground, while the other grayed out bars is when they're moving in the air. So in this case, the front left, the middle right, and the hind left legs are the legs that would either stroke across the surface of the water or take a step on a solid substrate, such as land. While the other three legs, the front right, middle left, and hind right legs, are the ones stroking through the air. These legs then alternate back and forth, hence the name alternating tripod gait. And in this dual here on the right-hand side, you can see that motion of it switching from one tripod to another in order to move on the surface of water or land. We then studied the amphibious locomotion of the Microvelia within these three aims. First, we focused specifically at the amphibious locomotion. We studied how the Microvelia adjusts its gait on different surfaces, whether that be water, land, things of that nature. So how's it adjusting its speed? How it adjusts moving its legs, things of that nature. In aim 2, we studied the propulsion and directionality and the specialized leg dynamics of water walking for the Microvelia. And so in layman's terms, we look at the role of each pair of legs and how it allows it to move on water, whether that's increasing its speed, whether if that's maintaining its direction, whether if that's just for stability on the water surface. Lastly, in our third aim, we focus on the interfacial fluid dynamics of vortex interaction in Microvelia. In this case, not only do we study how the Microvelia is moving on the surface of the water, we're studying how the water is moving along with it and the energetics behind that. And lastly, looking at any possible advantages it gets while it's moving on the surface of the water. With that, we then start with my first aim, the amphibious locomotion of Microvelia. And in this video, you can get an idea of the type of surfaces the Microvelia encounters in its natural environment. So here we have these two. One is a video on the left, while on the right is an image. So in this video here on the left, taken in Iowa, you can see this lake covered in this plant called duckweed. And this is a common substrate that the Microvelia and many other water walkers have to encounter when they're moving within their environment. On the right-hand side is an image of East Palisades Trail in Atlanta, Georgia. And in this image, you can see many different surfaces that the Microvelia has to encounter within its environment, whether that's the sandy banks that you see at the end of the pond itself, any possible leaf litter or sticks that may fall in the pond, or any rocks that might be peeking out from the pond. So all these different surfaces are surfaces that the Microvelia has to encounter and adapt its gait in order to survive and thrive in its environment. So with that, we then focus on the many different surfaces that the Microvelia encounters. And that's starting off with simply it moving on the surface of the water. So we're able to track the Microvelia through this technique called deep lab cut, which is a pose estimation software. So as we record the videos, afterwards, we then label the body parts so that we can extract data such as position and time, and then calculate things such as speed or angles of the legs at which they're moving. As you saw in the previous videos, the Microvelia is also known to move in surfaces covered in duckweed. And so we study these Microvelia moving in duckweed water combination at different area fractions. So here on the left, we have a video of a Microvelia moving on water with 10% coverage of duckweed. And on the right, we go up to 25% coverage. And you can see how the Microvelia is adjusting itself as it's moving between the duckweed and the water. Then we also study 50% coverage, where you can see that the amount of duckweed is more dense and that it's now mainly moving on the duckweed itself. And lastly, we studied it moving on sandpaper. Sandpaper is to replicate locomotion on the land. So we use sandpaper rather than a rock for better repeatability and replicability in our experiments and for future researchers to replicate as well. So the first thing we notice when we study these Microvelia across these different surfaces is its body speed and its leg speed when it's moving on water and these more heterogeneous surfaces or rougher surfaces such as sandpaper and 50% coverage duckweed. And what we notice is that when it's moving on water, it's moving actually about twice as fast as it normally does when it's on these rougher or more heterogeneous surfaces. And so on water, it's accomplishing speeds of about 50 to 60 body lengths per second on average for its maximum speeds. While on sandpaper or 50% coverage duckweed, the speeds are more closely to about 25 body lengths per second. And in this image here on the right of the leg velocity, we have an idea why. So when we look at the middle legs or the hind legs, we also notice that these legs are moving much faster on the surface of the water, also accomplishing speeds of about 50 body lengths per second. While again, for when it's moving on sandpaper or 50% coverage duckweed, we notice that the speed is half that. So since the legs are moving faster, then obviously the body is going to be moving faster on this surface as well. As for the upper legs, we see that the speeds are much more similar, and that's simply due to the fact that the upper legs are not the main legs for forward motion and propulsion when it's moving across its different surfaces. Then we look at the dynamics of the knee joint as it's moving across these different surfaces. The knee joint, also known as the tibiofemoral joint, but I'll refer to it as the knee joint in the future for simplicity. So when we look at the upper legs, middle legs, and hind legs, we can see these different trends. For example, we can see that for the upper legs, that the knee joint is a lot more active once there's any presence of solid surface, whether that's 10% coverage, 50% coverage, or even sandpaper. The way it's bending its knee joint is a lot more extensive. It's at a higher amplitude when it's moving on these solid or patchy substrates. And we can notice a similar phenomenon for when the hind legs are also moving on the surface, in that the hind legs are also bending its knee a lot more when it's moving on these substrates. And that's probably to do with like the way it has to pick up its legs when it's encountering these bumpy surfaces. As for the middle legs, we can notice mainly somewhat of a decreasing trend, and that's likely due to the fact that the middle legs aren't able to swing as much due to the coverage and the amount of solid surface coverage within the system. So it's not able to swing its leg as much. The exception is 50% coverage, and that's likely due to the fact that since there's so much duckweed, it has to do a lot more work to pick up its leg and therefore needs to extend and bend its middle legs more, which then shows this higher value here. So I have these videos here to play side by side so that you have an idea of what I was talking about in the previous slide. So you can see in the upper video where it's moving on water, how much more it's swinging its middle legs, as well as the fact that when it's moving on water, the hind legs are rather swinging from the hip rather than from the knee. Rather, when you look at it moving on duckweed, you can see how much it's actually using that knee joint to bend and move across this patchy surface of 50% coverage duckweed. Lastly, you can see how much more it has to extend its upper legs when it's moving on this surface. So one last thing you may have noticed is that when it's moving on water, the stride length, which is the size of the step, is much larger for the middle legs and hind legs than it is on the other surfaces. Even when you look at this illustration on the right, you get a sense for how much more extended the stride is for the middle legs and the hind legs when it's moving on water than when it's moving on a solid surface such as sandpaper. So we notice the opposite trend for the upper leg, in which the upper legs are actually extending themselves more and taking a larger step once there's any presence of a solid surface within the system. To summarize this aim, we notice that the Microvelia adjusts its gait, the alternating tripod gait, to move along these different surfaces. We notice that the Microvelia are faster on water than these heterogeneous or rough surfaces, such as these duckweed-covered water or sandpaper. We notice that the tibiofemoral joint or the knee joint is more active for the upper and hind legs when it's moving on any solid substrate. So we notice finally that the upper and the hind legs ultimately switch their stride when they're moving on water versus when they're moving on a solid surface, either increasing their stride for the upper legs or decreasing their stride for their hind legs when they're moving on these solid surfaces. While the middle legs show these the subtle decrease in trend in stride length simply because it's not able to swing the legs as it would like if it's moving on the water. With that, we move on to the second aim of this project, which was studying the propulsion and directionality within the specialized leg dynamics for water walking. Going back to this image in East Palisades, Atlanta, Georgia, not only have I talked about all the different substrates and all the different surfaces that you're encountering in this environment, another thing that the Microvelia has to encounter is the amount of different predators that it may face in this environment. So these predators can include the milky back swimmer, the water boatman, or any minnows that are swimming through the water. Of course, also any birds that might be swooping from on top. So all these different predators pose a threat to the Microvelia as it's moving in its environment. So we then ask ourselves, how does any possible injury from encounters with predators may ultimately impact its ability to move on water? And depending on which leg does it impact, how does that ultimately affect its ability to move on the water surface? So we study this through ablation, in which we remove the tarsi, and the tarsi is the foot. We remove different tarses from the Microvelia, whether that's the front tarsi, the middle tarsi, the hind tarsi, or a combination of the legs. And from there, we study how it impacts its speed on the surface of water, how it affects their ability to walk in terms of this rocking motion that we notice when it's moving on water. So if it's missing a tarsi, does this ultimately increase the amount that it's rocking back and forth when it's moving on the surface of the water? Lastly, we see how this impacts the directionality of the Microvelia when it's trying to move from point A to point B. Oftentimes, Microvelia are only moving either to seek a prey or to run away from a predator. So it does these really short bursts where it moves in a small, relatively straight line from point A to point B. So then we can see upon injury if there's a deviation from this straight line path. So first, we want to focus on if we remove the different pairs of these tarsi. So we focus on a non-ablated microvillia where it has all its tarsi, one where the front tarsi are removed, the hind tarsi removed, and the middle tarsi. And one thing that we notice in particular is that when the middle tarsi are removed from the microvillia, that it struggles to move on the surface of the water. We can see that its speed greatly diminishes. When we look at this figure on the right, we can see that its speed drops from the normal 11 to 13 centimeters per second that we notice from these other microvillia to about 2 centimeters per second. And in this video on the left, you can see again how much it's struggling just to move from point A to point B. Ultimately, because this microvillia cannot move on this surface, it exhausts itself and sadly perishes within 48 hours of the ablation. Now focusing on a different ablation type, we compare the non-ablated microvillia to the microvillia when it's missing both of its hind tarsi. And you can get a sense of what I mean by this rocking motion. When you look at the video here on the right, you can see that it's swinging back and forth much more as it's trying to move along the surface of the water. And so from this, we can reveal that the removal of the hind legs ultimately impacts this rocking ability. So when we look at this upper left-hand figure here, where we're recording yaw angle, we can see that when both hind tarsi are removed, that the microvillia is experiencing this yaw angle or this rocking angle of up to 20 degrees, much higher than what the microvillia would normally experience if it had all of its tarsi. And in this image in the bottom left-hand corner, you can again see this increase in rocking motion. When we look at a non-ablated microvillia, you can see that the track of the head along the centroid or the center of the body is a lot straighter than if you were to remove the hind legs. And we notice when we remove the hind tarsi, when we remove the hind tarsi, we notice that the head is rocking back and forth a lot more along this path. So when we look at yaw angle holistically, we can see that the microvillia rocks at an angle twice that amount when its hind tarsi are removed than to what we notice if the front tarsi are removed or if no tarsi are removed. We didn't study the yaw angle for when the middle tarsi are removed because ultimately the microvillia is unable to move on the water surface. So we notice for both hind tarsi that it's rocking back and forth at a yaw angle of positive to negative 20 degrees at its maximum, while for the front ablated or the non-ablated microvillia is more closely to about 9 degrees. So this helps us to surmise two things. One, that the middle legs are the main propellers in the system. They help to allow the microvillia to move forward and gain speed and move from point A to point B. While the hind legs act more as the rudders, they help to stabilize the direction so that the microvillia can move forward in a more straight line path. And you get to see more of this idea of directionality in this upcoming video here. When we remove the tarsi, the middle and hind tarsi from the same side, also known as the ipsilateral or same side ablation, we can see that as this video goes along, this microvillia starts to take this curved path. And this curved path is also shown in this illustration on the right. So when we compare a non-ablated microvillia to a microvillia where it's missing its middle and hind tarsi on the same side, we can see that the non-ablated microvillia is moving at a relatively straight line. Meanwhile, the microvillia with the same side tarsi missing are taking this really elongated, curved, semicircular path. So when we compare the same side tarsi ablation to all the other tarsi ablations, we notice a significant difference in its directionality to all other treatment groups. We notice ultimately that for most of the other ablation types, that the experience this D2 over D1 of greater than 0.9. And D2 over D1 is just this ratio between the displacement of the microvillia, so that specific distance from the very beginning to the very end, to the total distance of the path it takes. And so if it's moving in a relatively straight line, then this ratio should be close to 1. And if there's any deviation from this path, then the ratio will then be shown as less than 1. And so we can notice this significant difference from a D2 over D1 of 1, specifically just for the same side ablation. And so we can then say that this specific treatment case, we see that the directionality is hindered. So one more treatment group that we specifically had an interest on was the contralateral ablation, or when we remove the opposite middle and hind tarsi of the microvelia. One fascinating thing that we noticed is that on the first day, the same day in which we removed the tarsi, the microvelia struggled to move on the surface of the water. But within 24 hours, the microvelia soon relearns its gait, the alternating tripod gait, and is able to move on the surface of the water once again. So when comparing the ipsilateral ablation, or the same side ablation, to the opposite side ablation for these microvelia, we notice between day 0, when the tarsi are removed, to day 1 the next day, for the ipsilateral ablation, that there's no significant change in the speed. But for the opposite ablation, we notice that for the first day, the microvelia are unable to move across the surface of the water, showing speeds at about 2 centimeters per second. But upon the next day, it relearns its gait and is able to achieve a much higher speed at about 7 centimeters per second. And this again can be shown within the gait plots here on the right. We can see that for the first gait plot, in which I test these microvilli within an hour of it moving along the water surface, that there's no discernible pattern in its gait, in its walking, when it's trying to move across the surface of the water. But upon testing it 24 hours later, we can see that the alternating tripod gait pattern returns, and that the microvilli is in fact able to walk on the water surface. To summarize, the microvilli has these specialized roles for each leg pair. When we remove both hind tarsi from the microvilli, we see a higher yaw, or a higher rocking, when the microvilli moves across the water surface. When we remove the tarsi from the same side for both the middle and hind legs, we notice a hindrance in the microvillia's directionality, and is more likely to take these less straight paths when it's moving on the surface of the water. As for the contralateral ablation, or the opposite side ablation, we notice that it takes up to 24 hours for the microvillia to recover its gait in order to again move on to the surface of the water. We can then say that the middle legs are the propellers in the system. They allow the microvillia to move, gain speed, and move across the surface of the water. The hind legs act as the rudders. They help for steering and for directionality, while the front legs ultimately are then there for balance, so that they can balance themselves on a tripod on 3 different legs at any time when it's moving on the surface. If it was only balancing itself on 2 legs, it would be much more likely for it to tip over. So the front legs are necessary so that it has this balance when it's moving across the water surface. This then leads to my final aim for my dissertation project, which was studying the interfacial fluid dynamics of vortex interaction in microvillia. And in this video here, you can see that as the microvillia moves across the surface of the water, that it produces these beautiful counter-rotating vortices. And this gives us a sense of what this next aim is going to be about. So in order to get these videos, I use this technique called particle image velocimetry. Particle image velocimetry is where I take these particles, about 5 micron in diameter on average, and use them to seed the surface of the water. I then illuminate the surface of the water with a laser, and as the microvillia is moving across the surface of the water, we record the movement of these particles, which show the fluid flow, with a high-speed camera. And then we can visualize the fluid flow when the microvillia is pushing off against the water surface. And these vortices are emphasized using this program called Flow Trace, so that you as the audience could better see these vortices when they're created on the water surface. So one of the first things that we notice, and if we look closely here in the video on the left, is that as the microvillia strokes with its middle leg, the hind leg afterwards will step into the same location as the middle leg had just stroked. And in that, we can see that within these red circles here. So if we look at the video here on the right, we can see that when it first strokes with its middle legs, the vortices will increase in strength and then decrease in strength as it's moving along that stroke. And then before those vortices can completely fade away, so before the red and the blue can completely fade out, you can actually see that the vortices will re-energize, which is shown by the redarkening of the color of the vortices. And so we then aim to study the re-energization of these vortices or the vortex recapture as the Microvelia is moving across the water surface. From using PIV, we can track the vortices as the Microvelia is moving along the surface of the water. So I, along with Dr. Rohila, tracked the Microvelia when it's moving, and notice at one point when the onset of the power stroke is for the middle leg, when it begins to stroke across the surface of the water, when it completes that stroke, and then when the hind leg steps in at the beginning for the onset of that wake recapture. And then at point 3, the completion of that wake recapture when it completes that stroke and then moves on to the next stroke for the alternating tripod gait. So when we follow along these points from 1 through 5, we could get a better sense of this vortex recapture. To explain this plot, these circles are denoted as the circulation. The circulation can be seen as the strength of the vortex when the Microvelia is moving across the surface of the water. And that is also denoted by the right y-axis. On the left y-axis is speed, and speed is shown through the solid lines, the solid curves on this graph. So when we're starting at 0.1, that's when the Microvelia begins its middle leg stroke. And then the circulation or the vortex strength will increase until it reaches to 0.2 at that maximum vortex strength. And then from there, the vortex will diminish in strength until the hind leg then steps in that same area. This is the point of re-energization. From here, the vortex is re-energized to 0.4, where it's at its new maximum before the vortex then fades out again at 0.5, which is when the hind leg now lifts off to then start back its next step. And so if we were to continue to follow along the vortex after the Microvelia leaves it, we would continue to see the vortex decrease in strength until it reaches to a point of 0 circulation. But one thing that's important for this vortex interaction phenomena is the timing and the location of the leg when it's stepping in. And one thing we notice are these 3 different phenomena during this vortex interaction. One is re-energization, which is what we mainly focus on, in which we see the vortex specifically regain energy. Then we notice vortex annihilation, where it does still step in that same vortex, but it cuts at a wrong angle. So rather than re-energizing it, it slices through it and destroys that vortex. Lastly, we have no interaction, in which the hind leg simply steps in front of that vortex or steps behind it, and so it just misses it completely. And so we can map out all these different interactions or lack thereof and quantify how often it occurs. And we notice that re-energization happens at least 50% of the time. And it mainly happens as it's gaining speed. So at the very beginning, we're likely to see no interaction because it's just starting off to walk. And then as it's running close to maximum speed, we can see that the Microvelia basically jumps over its vortices that it's producing and misses the vortices it's striking in. And so that's oftentimes when we get this no interaction. Since we can't specifically control a Microvelia and how it moves, we developed a physical model in which we can control and tune to more closely study this vortex interaction phenomena. Specifically, we want to look at a better idea of how this timing ultimately impacts this vortex interaction. So through this physical model, we first control it with an Arduino controller. And the Arduino controller is used to control motor 1 and motor 2, which is attached to these arms, arm 1 and arm 2, which then stroke across the surface of the water. We then record that fluid motion using PIV once again. And so in this first video, we can see the first arm stroking across the surface of the water, it completing its stroke, and then the second arm stroking. And so we can change the time in which the first one lifts off, and then the second one starts its stroke. So delta T is the time at which the first arm lifts off the water surface, and the second arm first touches the surface. For negative times, then, that means that the second arm touched the water before the first arm lift off from the water. So in this first one, we can see that there's a significant time difference, and that ultimately leads to the vortices from the first arm to fade out before the second arm can reach them and interact with those vortices. But in these next two cases, the time is close enough that we do in fact get this vortex interaction phenomena. And from there, we can deduce either if we're getting vortex annihilation or vortex recapture. So in this case, when we look at these different plots, we can have a sense of when annihilation occurs and when re-energization occurs. So the first one, as I said before, the first case is no interaction. And we notice that the circulation, the peak circulation from the first arm and the second arm are about the same at near about 2.5 centimeters squared per second. When we encounter vortex annihilation, we then notice that the circulation for the second arm is diminished to half. And we believe that's due to the fact of these capillary waves that are created upon the stroke of the middle of the first arm that might cause this dissipation in the vortex. But if we time it right, which in this case is the negative 34 milliseconds, we actually notice that when the second arm strokes across the surface of the water, that we'll have a higher peak circulation at about 3 to 3.5. So if we time it right, we can then get this vortex re-energization and notice a higher energy within that vortex. We can then compare this back to the Microvelia itself. So Dr. Choi then looks at the relative pressure in the system as the Microvelia is moving across the surface of the water, specifically at the vortex, and compare it when it's at no interaction, annihilation, and re-energization. And we notice that specifically for the re-energization case, when it's first stroking with its middle legs, we get a relative pressure about 2 pascals within the vortex itself. Once the hind leg strokes in, we will notice this higher peak of almost 5 pascals, which again shows this re-energization that we're noticing when the hind leg perfectly does this vortex recapture phenomena, which is similar to the re-energization we notice in our physical model. As for the no interaction case and the annihilation case, we can see that the relative pressure is about the same for both the middle leg and the hind leg. So to further understand whether or not if this ultimately has a benefit to the Microvelia as it's moving across the surface of the water, we use computational fluid dynamics. And so Dr. Chandan Bose does a simulation in which we study this re-energization phenomena and compare it to annihilation and compare it to no interaction. So in the simulation here on the left, when we compare it at 0.5 seconds to 1 second, we can notice that at 1 second that the velocity field and that the velocities that we're noticing are higher and stronger within the system. So when we look at the thrust itself, specifically through coefficient of thrust, we notice that for the re-energization case, that we get this increase in thrust when the Microvelia is doing this vortex re-energization, hence vortex recapture. But when we notice this no interaction, we can see that we don't get this peak. And so this then, we can then surmise that vortex recapture does in fact give a benefit for the Microvelia when it's moving across the surface of the water from this coefficient of thrust. So to summarize this, overall, our model suggests that vortex recapture is beneficial for water walking at these scales. So the Microvelia's hind legs step into the vortex created by the middle legs and ultimately lead to this heightened pressure during vortex re-energization. Heightened pressure that we don't necessarily notice for the no interaction and the vortex annihilation case. We notice again with the physical model that the circulation is able to be increased and heightened during recapture when arm 2 strikes into the vortex created by arm 1 at the right time. Lastly, through the CFD model, we see this heightened thrust during recapture. And this heightened thrust is likely to the fact that when the hind leg is stepping in, it's encountering this virtual wall that ultimately allows the microvillia to get a better push off forward in this increase in thrust. Let's get that. To conclude, how does this ultimately apply to a robot? As I said initially, the inspiration for this was bio-inspired design. So I'll take you along these different aims to show you exactly how this can be applied to a robot. So in aim 1, we studied how the microvillia is able to adjust its gait as it's moving along these different surfaces. So we see how it's changing the dynamics of its legs, how it's changing its body speed, depending on what surface it's walking on. So therefore, any future roboticist can take the microvillia as inspiration for the idea of how it's able to adjust its legs when it's moving on these different surfaces. In aim 2, we study how each leg pair has a specialized role for walking on water. Then future roboticists can either design or program this robot such that each leg pair has a specific role, either if it's in directionality, if it's in speed, or if it's just in stability. In the third aim, we study how the proper timing and leg placement can possibly lead to a heightened thrust when it's moving across the surface of the water. Therefore, future roboticists can consider these constraints of timing and body size to ultimately determine when's the right time and right placement for these legs so that it can possibly get a heightened thrust within moving in its system. And so that's ultimately how all these different aims can be applied to a future robot that can be designed based on the microvillia.